Have you ever been confused about how to solve a problem in chemical engineering? Well, you're not alone. Many students feel overwhelmed when solving engineering complex problems, but don't worry. In this video, I will show you a systematic step-by-step approach which you can use to tackle any problem with confidence. Today, I will show you how to read the problem statement so we can understand what is being asked before jumping into calculations and into conclusions. Identify the key data that is given, the numerical parameters that we need to use to solve the problem. Identify and highlight the keywords and convert them into useful information. For example, the words steady state, adiabatic, negligible. What do they mean and how can we convert them into useful numbers that we can use to solve the problem? Then we're going to identify the key assumptions for the problem, which can be classified into explicit, the things that are given and stated in the problem, and implicit, which are the things that are not stated but are necessary to solve the problem. Next, we're going to write the equations systematically as we need to solve the problem, which are mass and energy balances and design equations as needed. Next, we're going to write the procedure for solving these equations in the correct sequence. And finally, I'm going to show you how to implement all this in Excel in a clear and systematic spreadsheet so you can use it to track errors and do have a very professional look. Let's go. Oh, by the way, I'm Dr. Aurelius Tamiti. I'm a professional chemical engineer with many years of experience in teaching and industry. My goal is to help students like you to fulfill their goals and build confidence in solving problems in chemical engineering. Today, we're going to solve a very simple mass and energy balance problem, which is the mixing of two streams to determine the properties of the mixture. And here is the problem statement. We have two liquid streams at different temperatures that need to be mixed continuously and adiabatically in a static mixer. They give us the information of the two streams. Stream A, 100 kilograms per hour with a temperature of 80 degrees and the properties, and same for stream B, 45 kilograms per hour and 35 degrees. And the question is, determine the volumetric flow rate in meters cubed per hour and the temperature and properties of this mixture. So I'm going to progressively unveil the procedure that we're going to follow. First, we're going to read the problem statement in full. Next, we're going to make a sketch of the process to visualize it. From there, we're going to extract the key data from the statement, identify the keywords, and convert those into assumptions and data. Write the key assumptions, explicit and implicit. Write the equations, in this case, it's mass balance and energy balance only. Then identify the knowns and unknowns from these equations. Then we're going to solve the mass balance first, calculate properties of the mixture of the stream. Then we're going to do the energy balance to find the enthalpy. Finally, we're going to calculate the temperature of the mixed stream from the enthalpy. And then we're going to calculate the final values that we need, which is the volumetric flow rates. And then we're going to summarize everything in a table format called a stream table. So here is the sketch of the basic problem. We have two streams at different temperatures, and here I already extracted the data from the problem, which is the volume, the mass flow rates, temperatures, and the properties of each. And the question is, what's the outlet condition? What do we get after mixing these two streams? And there is now some important information we need to identify. What are the conditions of this mixing process? And here I'm going to start using a highlighter. We need to make sure we identify the key information here. For example, keywords. They say two things: continuously, adiabatically, and they tell us static mixer. This is very important information because they tell us how the process operates. Continuously means steady state, no accumulation. Then adiabatically means this important thing: no heat losses. There is no heat going in or out of the system. And finally, a static mixer means there is no agitator. It's not a blender. So there is no extra work added from this in this process. And before continuing, I want to show you what a static mixer is. Here I have some pictures that would be very interesting. So a static mixer can be something as simple as a junction, a T-junction, which can be a simple tap, a faucet with hot and cold taps. So this is your shower. Then we have this equipment called the static mixer, which is basically a pipe that has some inserts which make the fluid swirl and twinkle inside. So it creates a mixing operation, but there is no agitation. It's just some plates that are inserted in the pipe. And finally, we have an inductor pump, which uses the Bernoulli principle, injecting one fluid at a higher pressure at a lower pressure, creating a suction. And then these two fluids get mixed at the outlet. And there is no work associated to it other than the flow of the two fluids. Now, if we continue, let's write which are the assumptions very clearly. So we know that there are two liquid streams. They are incompressible because they are telling us the densities, and they don't tell us that the densities change with temperature. So they are constant properties. Next, they tell us that the system is adiabatic, no heat associated. There is a static mixer, no work associated, no blender. They don't tell us anything about chemical reactions. So this is an implicit assumption. We can say that there is no reactions associated, no heat of dissolution or mixing associated with this. And also, we're going to assume, and that's another implicit assumption, that the fluids are completely miscible, which is not stated. Next, we're also going to assume, which is clearly stated, that this is a continuous operation. So there is no accumulation in the system. Now we proceed to write the equations of the mass balance. So we always need to start writing the generic equation of mass balance, which is accumulations equals inputs minus outputs plus generation minus consumption. In this case, we're clearly told that in this problem, there is no accumulation. Therefore, because it is steady state, this term is a zero because of steady state. So every time you write the assumption, you need to convert it into a number. And then you also write on the side why you did it. So steady state. So this way you will not forget why you did that. Now next, for the terms of generation and consumption, we are clearly told that there is no reactions of any kind. So these two numbers are zero. So no reactions. Okay. Then this converts the equation into the simplified form, which just have the summation of the two inlets, A and B, and the outlet stream C. And that's it for this simple mass balance in steady state. Now we move to the energy balance, which is a more interesting one. So similarly, we have the same general equation, accumulation, mass and energy inputs and outputs, generation and consumption. Same reasoning applies here, in which we have steady state, so accumulation term is zero, so steady state again, and there are no reactions and no heat of dissolution of any kind. So these two terms, again, become zero, because no reactions. And I can write it again, reactions. Okay? And this simplifies the equations. Important here, the energy inputs can be divided in two groups. The inputs related to the mass, as I stated it clearly, which is mass times enthalpy, and then energy inputs related to heat and work, which in this case is Q losses, if any. Since we identified that the system is adiabatic, I already said that this value must be zero because of adiabatic. And this way we have our final expression of energy balance complete. Please note that I defined and I left zeros here just to remember us that we had it this way, coming from the assumptions. Now we have the additional important relationships that we need to solve the problem. which can be grouped in different categories. First is the definition of enthalpy, which is reference value plus the CP times the temperature difference. CP is the heat capacity of the system. And every time we use a definition of enthalpy, we must define a thermodynamic reference. In this case, for simplicity, I'm going to choose 0 Celsius, and at that reference, I'm going to assign the value of 0 kilojoules kilogram Kelvin. And this is associated to a liquid stream. So this is something important here that I notice many times the students write the equation for enthalpy H equals Cp times T. Okay. This is a simplified version after applying the reference state. So if we write this equation again, complete Href plus Cp times the temperature difference, T minus T ref. Then if I put the values corresponding to the reference as zeros, then we get this final equation of Cp times T. And that's the reason why this equation can be valid only if we clearly state these assumptions of the reference state of 0 Celsius and 0 kilojoules per kilogram. Now, the other important information that we need is the expressions to calculate the mix properties for the outlet stream. So here I have the expressions for the weighted average in base of mass fraction for the density and the Cp. Here you notice something important is that I define that the change of mixing volume or mixing density change is set as 0 because no information is given about the mixing volume change. So I need to assume something. And in this case, for simplicity, I assume 0, which is pretty much okay for most industrial values. Now, other important definitions, remember the units. Density is mass over volume, but not only kilograms per meter cube. I can also calculate density based on the flow rate of a stream. So here I have kilograms per second or per hour over meters cubed per hour. So the time units must be at the same. They cancel each other here, so they will give me density information, the density property. So this is important because we can calculate it directly from a stream. The other important information that we'll need to calculate is the definition of the weight fractions of any stream or any component, WA and WE, which are defined as the mass of each component over the total mass at the bottom. Okay, so or the other definitions, if it is for a binary mixture or binary components, it will be one minus the other. And always for weight fractions or any other fractions, the summation of all of them must be equal to 1. And that's how this equation becomes valid. Now let's proceed to the solution steps. So you will see here that I need to calculate things not exactly in the same order that they appear in the equations that I need, because there are different parameters that I need to evaluate first. So this is the part that we need to create in writing first before doing any sort of numeric calculation. So, and it will change depending on the specific problem, because it will depend on what equations are required to solve. In this case, this is the steps. First, we evaluate the mass balance simply because we have the information of the inlet, so we calculate the total mass of the outlet of stream C. Then based on that, we can evaluate the properties of weight fractions because we have the mass of each component and now I have the total. I can evaluate these two. Based on this, I can next evaluate the density and the heat capacity of the mixture using the relationship we just defined. Then based on that, I can calculate now the enthalpies of each of the streams of the inlets, because I have all the information. So I have the reference, I have the Cp of stream A and the temperature provided of stream A, and the same for stream B. Next, since I have now the enthalpies, I can evaluate the energy balance and solve for the enthalpy of stream C, which is the outlet. And in this case, please remember, we defined that the heat losses are 0 because it's adiabatic. Finally, I have to use the enthalpy to plug it back into the expression for enthalpy for stream C, and from there I will solve for the temperature, which is the information that I'm needing. And one more thing that was not written here is we need to calculate now the volumetric flow rate for stream C, which I can calculate from here. So volumetric flow rate of stream C will be equal to the mass of stream C divided by the density of stream C, which I already have. So now let's implement this solution in Excel. Now let's start implementing the solution to this problem in Excel. The most important thing for working in Excel, particularly in engineering, is working in an organized manner. The best way to do that is to divide the spreadsheet in sections. What do I mean by this? First, I group the information by different types of data. For example, I group first all the constants together that are not going to change for my problem. For example, these are my thermodynamic references and the universal gas constant if needed. Then we have the fluid properties as required. These can be densities, heat capacities, or any other thermal conductivities, or even material properties as required. For example, thermal conductivity of a pipe. Things that are not going to be changing but are related to properties of fluids and material. Then we have the input parameters for the problem, which are going to be changing if required. So I will have the data divided in sections of input data, which I use a different color to highlight them, and then I will have calculated data with a different color. Then I will have a section of geometric parameters for a problem. For example, this can be pipe diameters, pipe lengths, or equipment sizes, or any other geometric parameters needed for the problem. Finally, we have other sets of parameters that might require. For example, here I included heat losses. Even though for our problem is going to be adiabatic, I decided to include it here because it's possible that the system might not be adiabatic, so we can play with this. Finally, I want to mention that it's always important to include a section of references in which you're going to put where you got data or equations or any other things you use to solve the problem. Because you might not remember later, and your boss will come 1 week or even 1 month later and it will ask you, oh, where did you get this information from? And you might not remember. So I do recommend that you always include reference to all the papers, websites, and books that you cite and that you use. Include them here. You can even do screenshots of the book or the paper, but also make sure to include the links so you can always go back to the original reference when needed. Okay? Now, I'm going to include here the calculations of the different flow rates in different sets of units because this is important as clients and people from different parts of the world are used to different sets of units. Some people might be used to meters cubed, other people may be used to gallons. So I'm going to include all the units possible that I might need so I can share this file later with different clients in different parts of the world. So let's start by doing a simple calculation, just changing the flow rate from mass in kilograms per hour to kilograms per second. So I'll just take this value and divide by 3600. So for changing to density, we just need now to take the same mass flow rate, kilograms per hour, and divide by the density. So it's important here that you use the constants associated in the cell. So it's important not to just hard code the number, for example, 1080 here, because what happens if this value changes for a different problem or for a different condition? So you will manually need to come in and manipulate this number in order to change it. But if you forget, then you're going to get the wrong data. So it's important to here always refer to a cell that is clearly stated as a property value. So in case this value changes, for example, 1200, this flow rate gets automatically updated. So you don't need to worry to manually come in and input the change inside the calculation cell. Okay, so I'll bring it back to the original value with undo. So then we continue. We now convert this flow rate to seconds. So I just divide by 3600. I am using 3600 here fixed because it's a fixed constant. This is never going to change. So in this case, it's okay for units conversion. There is another way of doing units conversion. For example, for these units that are not easy to convert because of the conversion factor being more complex, there is an important function in Excel that you can use that is called convert. And I'm going to show you that one now. So convert. So it asks you which is going to be the number that you want to change. So I'm going to start with the meters cubed per hour. And it will ask you from what unit you want to convert. So I'm going to look for meters cubed, which is available down here, all the way down. Cubic meter. So I double click and select it. So you see this is a text because it's inside quotation marks. Then it will ask me the next argument to which unit you want to convert it to. So I'm going to select the units that are related to volume, gallon. So notice one thing, once you selected your unit or original unit, Excel will tell you the other sets of units you want to convert to. It will give you already the summarized units available for volume that it has. It's important to note that this convert function contains plenty of units, but it doesn't contain them all. So you always have to check, and in some cases you have to do a manual conversion by inputting the manual conversion factor. And that's it. We have gallons, we close the brackets, and that's it. And now if I want to convert it to minutes, I'll just take this number and divide by 60. And that's it. So now I need to repeat the same process for stream B. But since now you see I have everything calculated, I just need to drag this and all the formulas will be updated accordingly. So you see now if I check on this formula, now it's referring to stream B flow rate, and same for the volumetric flow rate. It's now referring to the stream B density and the stream B flow rate. I organized it this way on purpose because I knew I was going to be able to do the dragging in that direction. So you have to be always vigilant on checking if when you do a drag a formula, if it is going to be pointing to the correct cell that you want. If not, you have to manually move it to the correct position that you want. So by doing that, you just simply hover on the edge of the cell that is highlighted in the formula, and then click and hold, and you will be able to move it to the correct cell. And then press enter, and the formula is saved. So you see now we have all the flow rates for all the stream in the different sets of units as required for the client. Now the same thing I will do with temperature. So I will convert to Kelvin. So I'm going to use again the convert function. Convert function from 80 degrees to temperature. There is degree Kelvin somewhere here. Okay. Degrees Celsius, and I want to convert to Kelvin. Celsius to Kelvin. And the same I will repeat for Fahrenheit. One more time. Convert. Convert. I press tab here to complete the writing, and you see it will give me an opening bracket. Select temperature from Kelvin. I can also manually type it. So I'm going to open brackets, F for Fahrenheit. So you will see it will start telling me which is the units that start by the letter F. And then I close. And then I'm going to change to Kelvin. Or, sorry. It's the other way around. I want to go from Celsius to Fahrenheit. And that's it. And then I replicate to the other. And that's it. I have the information. Same here I can do for the heat loss. So you see I put as an input parameter the heat in kilowatts. But for my energy balance, I might need to use this information in watts. So it's better to always do the conversion in advance instead of doing it in the calculations in the energy balance. So I'm going to just convert whatever value that I have here, in this case 0, times 1000. And that's it for all the input parameters. Now let's go and complete the mass and energy balance calculations. We're going to start with the mass balance. So this is very simple. From the solution steps, we saw that the mass balance of stream C is just the summation of streams A and B. So I'm just going to proceed with that. So I just prepared the information I needed here. So this is going to be a calculated cell. And I'm going to use the function sum. So this will be just sum of these two flow rates. So I'm going to select the range that I need. And that's it. It's a summation of these two values. I close the bracket, enter. Then I can convert it back to kilograms per hour. That's one alternative. So I'll just take this number and multiply times 3600. Okay. Or I can do alternatively, or as a check, I can do again a summation of the flow rates already in kilograms per hour. And then I can either close the bracket manually or just press enter here, and Excel will automatically add the closing bracket to the formula. So you see here, I confirm that the values are correct, are the same. So now we can continue with the other calculations, which are the fluid properties. Now moving down to the fluid properties of the mixture stream. So I already prepared the frame of how we're going to work. So the first thing we need to calculate is the weight or mass fractions of each of the streams. So now we have the total flow rate. So the definition of the weight fraction was the mass of one component or one stream over the total mass. So I just need to start assembling the formula. It's going to be the mass of stream A. I can use whatever number in kilograms per hour or kilograms per second, as long as I keep the units consistent. So I'm going to use the kilograms per hour. So it's going to be this value divided by the total mass. Okay? And that's it. And I already have it in percentage format. So here, then I will move it to the next one. And then I get an error. Why is that? The problem is when we drag the formula, all the cells were moved as well. So you see here, I got correctly the numerator, which is 45 kilograms, but then I don't want this to be in the blank cell. I need to be back into the original cell, which is C133. So I have two alternatives. I can either manually move it back, or I can actually fix the formula and do it correctly, ensuring that the denominator remains constant in the fixed cell. So that's what I'm going to do. So I'm going to delete this, and I'm going to modify this formula, and I'm going to ensure this cell, the denominator, is pinned. I'm going to use that using the key F4, which is for creating an absolute reference of the cell. And you see here that I'm adding dollar signs in front of the letter and in front of the number of the cell. And that will ensure that when we drag the formula, this cell remains fixed in its position. So now let's move it to the next. And now let's verify we have correctly kept the denominator in the position we want. I always do a check at the end to verify if these summations for weight fractions are always equal to 1. So I'm going to add sum, and then sum these two values, and that adds up to 100, which is what I always need to verify. In some cases, depending if the numbers are not correctly normalized, there might be a problem. And this is a way to spot a possible error. So all these checks are always important to do. So next, we need to calculate the properties of the mixture using the weight fractions. So let's start with the density. So here you see it's a combination of a product of property times weight fraction plus property of the other stream times weight fraction. So there is an interesting function in Excel called SUMPRODUCT, which actually does that operation. And I'm going to show you how to use it. So it's called SUMPRODUCT. it will first ask you which is the first array or first range of data that you want to do. So the first range of data is going to be these weight fractions that are together. And it will ask me the second array. So you want to take each of these numbers and you want to multiply them to which other numbers? And in this case is density, which is this constant parameter that I have here. So this is the other advantage of putting the constants here as separate cells and not hard-coded in the system. So I can reuse the same value in multiple calculations throughout my spreadsheet. So now I'll select this. And then I close my bracket. And that's it. That's the density of the mix stream. Then let's repeat for the heat capacity. Again, SUMPRODUCT. First array is the weight fractions. Now, second array will be the heat capacity. So I bring this down to the cell. So you see, first array, take each of these numbers and multiply them times the other sets of numbers. Something very important is these arrays must be of the same size. So if it is a 2 by 2 or 2 by 1, the other array must be exactly the same. Otherwise, it will give you an error because it's trying to say, hey, you're giving me more numbers on one side than the other. I cannot complete the multiplication. So you must always ensure that these arrays are of the same size. Now we close the bracket. And here we have the heat capacity of the mixture, already in the units we want. Next thing, which is one of the questions that were asked in the problem, is calculate the volumetric flow rate of the mix stream. We already have the density of the mixture, so let's just use it. So I'm going to take the mass flow rate of the stream, which we already calculated up here, and we divide it by the density that we just calculated. And that's it. Now we just need to do the unit conversion same way as we did before. Take this one and convert to seconds by divide by 3600. Next, I'll use again the convert function to convert the meters cubed to gallons. So I go here, meters cubed per hour. I'm going to be consistent if I need to keep the denominator units constant, because convert function only works well with the numerators. It doesn't work well with the denominators. So I need to keep the denominators constant for using this function. So I'm going from meters cubed. So you see here I have meters cubed. I'll start typing. I already found it. Meters cubed to US gallons, which is, oh, something important. We have gallons here. You see this one. This is the US one. But there are different types of gallons. So we have also available the UK gallon. So important to be careful which one you're using. So in this case, we have selected the US. So double click and close bracket, and that's it. Then I'll divide it by 60 to get it to minutes. And good, we have completed the first part of the exercise, which is just getting the volumetric flow rate. Next is the temperature. So now we're going to continue with the energy balance. Now, moving to the energy balance, the first thing we need to evaluate is the enthalpies of the input streams A and B. So here we're going to use the thermodynamic references as needed. Even though they are 0, I'm going to keep them as a part of the formula, because I might be able to change them later on if required. So let's start by looking at the reference. So I scroll up and I found it, href. And this one I want to make it a constant or fixed cell. So I'm going to use F4 to fix it. Now will be this plus the heat capacity of stream A. So I will go back up and look for it. So here we have it. So again, this is very important to be able to have it as a cell so I can refer to it later on in multiple calculations. Now this one times the temperature of stream A. It's 80, oh, forgot open brackets, 80 minus the reference of temperature, which is this one. And this one will also be a fixed cell. F4, close bracket, and that's it. That's the formula. And then I can scroll it back to the right, and I get the number. So you see again that the references remain in the constant place because I use the absolute reference value of $signs. So here you see them, they're fixed, and the other properties have been correctly moved to the stream B parameters. So something important here is what we need to check are the units. So I always need to verify that the units are correct. So CP is in the units of kilojoules, kilograms, Celsius in this case. Kilograms, Celsius. This Celsius is defined as the change of degrees, not the actual degrees. So that's why on the bracket I have a difference, change of temperature, Celsius minus Celsius. So this is a difference, a delta. So and that's what makes it possible to be able to cancel this unit in the numerator with this unit in the denominator. Now, continuing with the energy balance for stream C, the first thing now we need to evaluate is the enthalpy of stream C. So I have prepared here the structure of what we're going to evaluate. So from the equations, you remember we need to solve for the enthalpy first from the energy balance. So it's this large equation, which has all these terms in the numerator and the mass flow rate of stream C in the denominator. So I'm going to evaluate first the numerator separately because it's always better to evaluate portions of large equations separately in order to see if we have made any mistakes or so. So it's easier to track. So let's evaluate the numerator. So it's first the group of mass flow rates and enthalpy. So here we can use the sum product formula. So let's do it. So sum product. Here it is. So I'm going to look for the flow rates in kilograms per second. So I get my results in kilowatts to make it consistent with the units of heat loss, which are in kilowatts or kilojoules per second. So let's go here. Mass flow rates, kilograms per second, comma, enthalpies of A and B, we just evaluated. And this is the first group. And I close the bracket. I can evaluate this now. And this will give me only this portion, A and B. Now I can again come here and modify the formula, and I put minus, and I'll add the heat losses, in this case in kilowatts, just to make it consistent with the units. And that's it. That's the entire numerator of the formula. Now, in order to evaluate the enthalpy of stream C, I need to divide that number by the mass flow rate of C. So I'll just do equal again. This divided by MC, which is up here. And I have to make sure that I do it in kilograms per second, just to be consistent with all the units. And that's it. I ensure that this value is in kilojoules per kilogram. Then we need to solve for the temperature. And I'm going to use now the definition of enthalpy that we just used before. So we're going to go back. Temperature of C is going to be reference plus all this group. So let's start with the reference temperature. Reference temperature, I'm going to fix it again. F4. F4 plus. I'm going to open a bracket here for the numerator. It's going to be HC minus HREF. HC minus HREF. I go up and I find HREF again, and I fixed it again, F4. And then I divide this bracket by the CP average of C that we calculated before. CP of stream C, which is here. This one. And that's the temperature. So now, if required, I can convert it to other temperatures. Let's do it again. Convert it to Kelvin, for example. So I have these ones. I have quotation mark, Celsius, degree Celsius here. Celsius to Kelvin. Here it is. And we repeat for Fahrenheit. Convert Celsius, open quotation mark, Celsius to degree Fahrenheit. Close brackets. And that's it. Now, the only thing left for this problem is to create the summary table. So the summary table here will contain key information of the streams. And this is called a stream table. And this is a basic table that always needs to be produced for any process flow diagram. So, and it contains mass flow rates, volumetric flow rates, temperatures, and any other relevant properties of the stream, like density, heat capacity is possible, but also can contain compositions, relative humidity, for example, if it is gas stream, or elemental compositions if you're tracking a specific element or component, like concentration of salt, if you require. So that will depend on the specific problem, the information you need to show. So here, now we're just going to collect all the information together to show it as a table. So I'm just going to look for my original values in kilograms per hour. So I have to go all the way up. And I will repeat the same for the others. So one by one, I have to do it. It can be a bit boring, this final assembly. And I continue volumetric flow rate and so on, as we have calculated before. And since this one, I put them in the same sequence, I just need to drag down and I will have them exactly here. Now for the temperature, I will do the same. I have them already in the same order, so I'll just pick the numbers once. Oh, I only have Fahrenheit, so I'll just have to pick directly Fahrenheit. I didn't use the Kelvin, so I might eliminate it if I want to, but I'm just going to keep it. Then we have densities that these ones are corresponding to the original data. So I have to go back here. Density and CP are together. So this one, I'll just drag it down. And for streams A and B, I know the values are next to each other. So I can just simply stretch it to the side, and I have all the information for stream B. Now we need to go and look for stream C. First, I need to do a little bit of formatting. I'll just add this line just for presentation to show that these are my input streams and these are the output streams. This is not necessary. It's just for looks, to make it look more professional. So stream C, let's look for the information, the mass flow rate that I calculated in kilograms per hour. Then I have the same kilograms per second, mass flow rate, kilograms per second. So in this case, they are inverted, so I have to make sure I select them properly. And then I look for the different properties. Volumetric flow rate. These are in the same order, so I will be able to drag them down. So I just drag down here. Then I look for the temperatures, which is the one that I calculated here, 65, and the same value in Fahrenheit. And then the properties, which are above, density and CP. And this is it. This is the final product of our work, is this stream table. So you see that I need space for working, doing these calculations that might not be in the most intuitive sequence every time. But at the end, you always need to summarize it in one way that you can ensure easy way of presenting your data to the client. And this is the most important thing, because this is what you're going to share at the end. You're going to just copy paste this table into a report for your client. Well, I hope you enjoyed this video. I'll put a link below with the file in the description so you can download it. And if you're also interested in having a session with me for private tutoring and consulting in any problem you want to solve, you can also check my personal website below. And please don't forget to subscribe, hit the like button, and hit the notification bell so you can get my videos next time when they come up. Thank you for watching.